is a topic that primarily has been studied in the machine learning and computer vision communities. But what's interesting about it for this course is this is inherently symbolic structure being extracted from images. And what we're starting to see a little bit of is how can we expand on scene graphs using different forms of symbolic reasoning. And the current thing going on there is more along the lines of semantic knowledge graph alignment. We'll talk about some of that. So posted online are a few associated papers. So we'll talk about some basics. There's a somewhat recent survey paper on this topic that's pretty decent. We'll talk about action genome, one of the big data sets used in this. And then we'll go into some work on, actually we're going to talk about using transformers and then adding background knowledge. So a slight typo, I changed the second last. So anyway, scene graph basics. So, you know, here's your image, and here's an example of associated scene graph. And really quickly, we'll go over some of the key terminology that is used. You see the word object, which in logic terms, you would probably think of these constants. These are items that are objects in the picture. In the vision world, there are things that are generally going to be associated with bounding box. And they form the nodes in the graph. Now then there's edges. Okay, so edges, the edge between the nodes just exists if there's any type of relationship. And this is kind of a key distinction is inferring if two objects are related in any way versus characterizing their relationship. So when I say edges, I'm not talking about near, I'm just talking about there's a direct relationship between tree and road without specifying what it is. And finally, what people who do a lot of this work refer to as predicates are the relationships or the labeled relationships. And here you see words like near, on, in front of, or behind. Okay? This particular scene graph is a little bit boring because words like near, in front of, next to, they're not very descriptive. Ideally, you would like things like the car is parked on the road. The car is adjacent to certain trees and stuff like this. So the first thing that you'd want to do with scene graphs is actually linking. And so we'll talk a bit about some aspects of the construction process. And some of these steps can be used in different ways. So first is what a survey paper called link from I to X. And this is going from image to object features. So this is simply applying something like a CNN to the image and getting a bunch of features from one of the top layers of the CNN. The next is going from the feature, from the bounding box to the object class. And so this is actually giving a class label to the objects like car or tree. And so far, these are pretty straightforward and nothing special. Pretty much any business problem, you're seeing this. So next is the predicate classification. The first is looking at pairs of objects and inferring the predicate. But you can also look at pairs of bounding boxes and use that information. You can think of the top one as kind of purely symbolic. The bottom, the next one here is more dealing with kind of the features associated with those two objects from the uppermost layer of the perceptual model. then even going one step further, you may also be interested in actually mapping the portion of the image to a predicate. So you could think of a person, drinking a can of soda. Okay, that configuration of what the person is doing with that can, that predicate would be something that could possibly affect as well. So some of the key challenges, well, the learning algorithms actually construct the graphs. This is a hugely challenging problem. And the results you'll see as we go through this, they're not quite to the point, I think, where this can be impactful in a lot of real world stuff. Another challenge is the use of prior knowledge. What if I have something like a common sense knowledge graph? How do I leverage that to improve results? And then another challenge is long-tail distribution of visual relationships. So we showed you that scene graph at the beginning of the report. How do you go from a scene graph that says person holding a cup of coffee to person drinking a cup of coffee? How do you get something more descriptive like that? And part of the problem is you have a long-tail distribution of visual relationships. If you have a data set of ground truth scene graphs, you're going to get a whole lot of examples of next to, in front of, and things like that are not very useful. You're going to get much fewer samples that are going to have these more descriptive relationships that are actually, in many ways, they're more interesting. So there's, over the years, there's been a few different approaches. Kind of a traditional thing for scene graphs in the vision community, especially prior to the neural network area, has come from conditional random fields. Embedding approaches, also at one point were quite common. This is a lot due to the widespread use of embedding approaches, things like knowledge graph reading. But really, most of the state-of-the-art is going to fall into categories like this. And all of these architectures, even though I wrote for GNN transformers, there's been actually variants of all three of these that have used attention heads somewhere in the architecture. So the use of prior knowledge. So here, and we'll talk more about this in detail, but basically when you produce a scene graph, how do you take something like a knowledge graph, and we'll talk about this with knowledge graph later, how do you use that to augment? But knowledge graphs are not the only way that it's been used to augment scene. So we could also, there's also things based on statistical prior, things that normally co-occur together, or graphs that deal with language and semantic meaning of the language, in addition to common sense that's out there as well. Talking a little more on the problem of long-tail distribution. So bias generation. So when you hear the word from the scene graph community of a biased scene graph approach, they're referring to a scene graph model that is trained on the data set that's something like this, where you see on as bearing are very strongly represented, and even getting something like walking on, you're getting a very small proportion of the data already. And as a result, you get a lot of ons and years and has in these biased scene graphs. When you're unbiased, now you start seeing things like spark drive in front of a little more descriptive than the other. And when you get to downstream tasks, which we'll talk about in a moment, having more descriptive relationships has obvious implications. You can think of an image captioning, for example. Image captioning is not going to do too well. This is what we get. It'll do much better the relationships are more descriptive. So speaking of downstream applications, so here's a summary and a couple we will talk about. Visual textual transformation. So there's been some work on actually image generation using scene graphs. Captioning is another interesting area. Used for image retrieval. Now this one's really interesting because with image retrieval, it reduces an image retrieval problem to kind of a graph comparison style problem, which has some advantages. Visual question answering, visual reasoning, so this also includes activity recognition, where you have, here's a picture of two people in the scene graph, and it includes the family. 3D scene graphs, this deals with when you have something like hierarchical structure, you have different buildings on a street, and different rooms in the building, or different floors in the building, different rooms in the floor. And so this type of scene graph reasoning is application. And then one area that is kind of special is human-human interaction or human-object interaction when you're reasoning about a human interacting with another human or human interacting with another object. So talking a little bit about these. So, we've all seen kind of fail with stuff like DALL-E, where someone gives it a caption and generates an image and it screws it up. And if you ever read anything by guys like Gary Marcus, they'll quickly point out to stuff like this and saying, hey, this is evidence, it's not really reasoning about the story. It's just kind of generating whatever. It's obviously wrong. The person, the animated character, is also the back of the chair, sitting on the chair. And here you have this weird thing with the glasses and the balls of puff coming out of the person's neck. And so the idea is that, hey, if you generate this from a scene graph, you can start avoiding this. Now, the work here is very nascent, and the images that, at least in the few papers that I was looking at putting together, are like very low resolution. But it is an interesting concept to overcome some of these difficulties. So image captioning is, I think some of this work is very interesting. And what you have here, so what they're showing in this slide is the image scene graph is what is actually returned by the algorithm, and the second scene graph is the ground truth scene graph. And then they compare the ground truth to what the scene graph algorithm provides. But here's an interesting thing. The scene graph-based captioning is not supervised at any description of the image. So I think that's really interesting from the standpoint of data efficiency, not having to rely on pre-labeled images. And also, there's probably a danger with having pre-written captions on images that come from a very large data source, where some of them may be inaccurate, or they might be talking about something that's not really in the image, but using it within on the surface. And again, kind of like image generation, here you're, what they call unpaired. The unpaired description is coming right from the scene graph. So there is like a little bit of trace of explainability going on here. I believe the method in this paper that we use is something like that. So the other application areas that we have listed, I think we talked about all of them. But the point being is that the idea with scene graphs is that it can enable a variety of applications, and it's giving you a kind of a symbolic underpinning of what's reasoning, some sort of reasoning process. Now, again, to date, a lot of these downstream applications, they use scene graphs and put it into a GNN or something like that, which begs a little bit of the question as to why even bother, what's that actually giving. But then I think the applications that deal with things like, say, information retrieval or database query, where you can kind of leverage that graphical structure in a direct way, those have also some definite utility. So I'm going to talk about one of the data sets and use this kind of as an exemplar at Genome. It's the video version of another popular data set called Visual Genome. And talking about this is not just about the data set, but also gives you a little bit of insight into the methods and difficulty of things. So if you have a video, you can find a scene graph for each frame, and you have this kind of time evolving scene graph. And notice that the objects within each of the frames, for the most part, there's not a whole lot of change going on between them. Here they're showing the relationship. And what's happening in this very short video clip is the person in the sofa over there, the relationship is changing. So right now, the person next to, then the person is in front of, then the person sitting on, so the person and so on. So the idea with establishing this data set is they want to provide a somewhat large data set where the videos had good annotations for both objects and relationships. And for that kind of point that's getting across. Now notice with the relationship, this is a log-based scale, and so this does suffer from the same kind of problem where you have things that are in front of, not looking at, holding, they are, occurring much more, and then when you kind of get down to some of these other ones, they're occurring a lot less, because we do multiple 10 years by counts of how often those relationships occur in the data set. So they establish kind of a baseline for this sort of scene graph reasoning. That's actually a little bit more of a framework. So first, we're going to use a state-of-the-art method for identifying the scene graphs and the individual scenes. And then they're going to formulate what they call a feature. They're going to formulate this FBO, but they call it a feature bank. There is scene graph feature bank, FSB. But it's a set of features that after you have the scene graphs for each individual scene, you now have the series of objects and everything in that, and you use that to use these feature vectors that a feature bank that's across the entire video. So think of this as kind of a macro thing for the whole video. Then they have a clip. They're going to use clips. Take clips of the video and expect features to move to them. But that's being done through a 3D convolutional neural network. And so the scene graph features that are across the entire video with these features from this CNN that are for individual clips, those are then combined together with the bank operators. Some of the authors will say that it's basically using for to define an action label. So here we've got scene graph usage over time to identify an activity sitting on a chair from a couch and so forth. So what they looked at here is they looked at a bunch of baseline methods and they looked at pairs, and they the scene graph prediction with their method was trained on action views. It's really actually the difference from the other methods that they have. And so with doing that, they are providing better performance. They also show that if you have the actual scene graph, the mean average precision goes up to 60, but they also say that that's not, like a theoretical limit necessarily, because the scene graphs that they used in that were only partial. They didn't have all these. The other interesting thing that they did was they started looking at this from a two-shot perspective, where they had limited samples from the data set that they were using, or training data from the data that they were using the prediction on. So essentially really moving on action genome to kind of provide, very strong pre-trained models. And so they're actually getting what we don't have to, not looking for, we're actually getting stuff that's not too far off from the 44 mean average precision. So they looked at comparison across different scene graph methods. And so looking at the things to evaluate is they look at the recall numbers at 20 and at 50, but they had a couple of different scenarios that were interesting. FPGen is the input is the raw images, and everything needs to be predicted. Bounding boxes, objects, and predicates. Then SPCLS, we're going to say the system has ground truth for the bounding boxes, and the spread TLS, we're actually only going to look to predict predicates. And what's interesting here is you can start to see how the different components, impact the overall accuracy. So predicting the predicates, your recall numbers are still like both 50. And this should be a big hint to us that we're dealing with a pretty difficult problem, because again, these are like recall numbers at a certain amount. So I don't think in other applications probably would not be a very tough method. But I think and of course they do go down as you do some of these things. But what's interesting also is you lose about 10% without ground truth bounding boxes. So even the base perceptual model, even though as a community today, in computer science, was really good at image recognition in the last few years of research, even that is a significant contributor to the problem. And this is, I think, part of the reason why scene graphs are really difficult, because you have to get the objects identified properly. You have to not only know where they are, you have to know what they are. And on top of that, then you have to determine the relationship between them. But if you have like an object that's not really there, or you miss an object, you're going to miss a whole bunch of edges and predicates associated with that lost object. And so this is where things get really challenging. So I'm going to talk a bit about one of the more recent methods for this that in some ways is part of the state of the art. This is scene graph generation with transformers. And so one thing that they point out here is that prior to this work, they're saying that the consistent state of the art paper rely on assuming that there are edges between all objects that are recognized. So you do your convolutional neural network or your vision transformer, you have a bunch of objects, you make a complete graph over that object, set of objects. And then you go and you label all those edges. So obviously, as you get more and more objects in the picture, this is going to become pretty bad computation. The other thing they say that is they're ignoring the semantics between nodes. Okay, so there could be two things in a picture. So say me and like your water bottle over there. If you took a picture of this room, both me and the water bottle would be in the picture. But I have no relationship to that water bottle. And so this is totally ignoring that semantics. And it's very easy to, have something that, give some arbitrary edge relationship. That's not really adding any value. They also say that these issues become aggravated by bias and prediction. They point out that the existing unbiasing techniques that usually deal with doing something about the data set itself, they're relying on the same approaches where you're getting the complete graph. So the key idea here is the inference of the edges becomes a step by itself, which I think is kind of a neat idea. So they're, instead of just going right from objects to predicates and assuming and having this kind of hidden assumption of a complete graph like most other work is doing, they're saying, hey, we're going to take a minute and we're going to see if these relationships actually are there. So the first step of this is object detection. And they call this, so they're detecting all the objects using some, state-of-the-art perceptual methods. And they say we're detecting the objects, so the bounding box, and hypothesize labels for the object. As you see in the next step, they're actually going to end up defining. And nothing about relationships are being detected at this point. Straight up, using faster RCNN or whatever to just find the objects and say, hey, these are the labels that you think belong. So the next part, and I'll go into this in more detail in a bit, but just to give you a high level view, is iterative graph generation. The idea is over that set of initial objects, generate a directed graph. And the edges just mean that there's some plausible relationship. And they're doing this with a decoder approach, and they're building the graph by adding nodes one at a time. And yeah, I think we'll have some other slides on this. So we'll go back to it now. One thing is this approach results in an adjacency matrix over nodes, and then they have a thresholding parameter where any relationship in the adjacency matrix is the threshold. So now that you have a graph, now we're doing the relationship prediction, where essentially they're predicting the relationship based on the nodal features that come from the labels that are reassigned to the nodes in this step here. Because those labels are updated, you have features that go along associated with those labels. You have no, that's actually the semantic feature. These apps are the features from the first. The bounding box itself from the image, and FG, which are the features from the graph that came from the second step. So just to make that clear, features from the initial perception, features from the label assigned to the nodes that are updated here, but instantiated there, the bounding box from the image, and the graph from there. So overall results, bottom line is that unbiasing, they achieve state of the art. Without unbiasing, they achieve state of the art. Some of the tests they come within range of some of the better performing algorithms that use unbiasing. What's also interesting here is that edge sampling. So in the training data, they can they limit the number of edges that get sampled, and they see that they don't need to sample. They can get stable results by sampling only a fraction of the pairs of edges. They also looked at this in terms of zero-shot evaluation. And of course, the numbers here are end up being extremely low, but they still outperform some of the other approaches. All right, so then we'll go to the final piece, adding background knowledge using knowledge graphs. So as we talked about earlier, long-tail distribution over relationship prices, and we have going from biased to unbiased graph. The idea here is let's leverage some common sense knowledge from the common sense knowledge graph. So the basic framework, if you're doing scene graph generation, you produce a scene graph. Then going through this process where you have the knowledge graph and the embedding of each node is compared with triple in the knowledge graph to check for alignment. I'll do that in a moment. And then, of course, then pass the downstream reasoning. So whatever application you're using this for. So to go through, once a scene graph is created, there's a two-step process. There is a refinement step, and then there is an enhancement step. So first, the refinement step. And so you have your scene graph F, triple in the scene graph. You look at the knowledge graph embedding of the two nodes in the triplet in the scene graph. So we're seeing what the embedding of these two guys in the scene graph looks like in the embedding space induced by the knowledge graph. Then we also have the bounding box of the two nodes. And we're computing these metrics based on that. So we're looking at the similarity between the two nodes based on the knowledge graph. And we're looking at intersection over union between the bounding box. So if the similarity between both of the nodes is less than some threshold, and the IOU is also less than the threshold, we're going to conclude that they're not redundant. Because if the two nodes are both semantically similar and the bounding boxes are overlapping a lot, we're throwing it out. So the next step is a little more interesting. It's improving the scene graph with the knowledge graph. So here, for each node in the scene graph, we find the knowledge graph embedding again, just like what we did in the other algorithm. And then what we do is we're going to find all triplets in the knowledge graph that contain that node. So for each of those triplets in the knowledge graph, one of the two nodes in that triplet has to be the same as the node in the knowledge graph. So this step is just figuring out which one we're going to take. And then when we look, the cosine similarity between the two embeddings is within a threshold. Then what we're doing is we are attempting to triplet from the knowledge graph to the scene graph. Because we know we have one of the nodes of that triplet is already in the scene graph. So we're throwing this new edge and potentially a new node into the knowledge graph. It's already there. So it's pretty straightforward. But the results are pretty interesting. So all the typical recall it K, and new recall K, everything is increasing as a result of the process. You also see some evidence here, although I would like to explore it further, that some of these lower frequency predicates now jump up a lot. So we can tell this by visually looking at it, but I think it will also be good to quantify this a little better in the results. So then looking at downstream tasks on image captioning, there's a state of the art, they're either exceeding or right in line with the state of the art. Nothing. And so just to wrap up today's thoughts on scene graphs. So, this is still a very active area of research. There's papers coming out all the time. To date, most of the work is focused kind of on the perception level. As you saw in some of the results, like task of predicting predicates is hard, but at the same time, identifying the objects themselves, if you're even making small mistakes there, they get amplified as you go to later steps in the pipeline. Biased data sets, result in uninteresting relationships being predicted. And this also hurts recall a lot too, because you have fewer predicates of different types. And so, logic, knowledge, neuro symbolic AI has not been applied widely to this area, but I think what we saw in the SWJ paper at the end is kind of an indication of what's coming. I think that, as more, as there becomes more interest in kind of the neuro symbolic community on this, we may see some different kinds of results, or the use of, scene graph perceptual work such as a transform model guide is kind of a base model to do other things. All right, so that about wraps it up. Any questions?